We're going to continue where we left off. Chapter 5, we left off at Theorem 10. Limits of continuous functions. Remember, if a function is continuous, then we can take composite functions. Remember what composite functions were? Those are the f of g's and the g of f functions. Let's say we had two functions. F of x is 5x, g of x is 3x plus 2. If I ask you f of g, what that means, it means the function f of the function g. What that means is anywhere I see an x in my f function, I put the function g of x. So here's f of x, it's 5x. So anywhere I see an x, I put a g of x. What is g of x? G of x is 3x plus 2. And you work that out. 5 times 3 is 15. 5 times 2 is 10. So there's my composite function f of g of x. And then g of f of x says the g function, and inside there, in place of x for the g function, I put f of x. So g of x is 3x plus 2. So anywhere I see an x, I put f of x. And f of x is 5x. And work that out. 3 times 5 is 15. And there's my final answer. So that's how composite functions work. Review of algebra. Now, how does this relate to calculus? If both f of x and g of x they're both continuous functions, meaning they have no holes, they have no asymptotes, they have no oscillating functions, then we can take the limits of those functions. The Theorem 10 says this, and I'm glad we're using this one because it's going to help us do the examples. We'll see how, if we can interpret what this theorem says, then the assignment problems will be no problem. So if we have the limit of f of x as x approaches c equals some number b, remember, f of x and g of x are continuous functions. So the limit of f of x as x approaches c is really f of c, which equals some number b. That's the limit. Then, if g is continuous at that point b, then what we have the limit of the composite function f of g of f of x as x approaches c is really, we'll work through this one, is g of f of c, because we're going as x approaches c. What is f of c? F of c is b. So the limit of g of f of x as x approaches c is actually g of b. Now, what does that mean? We take the limit to find the input function. Once we do that, we take the limit to find the inside function, and then we just take the outside function. You notice it doesn't say take the limit of g. It says take the limit of f of, basically what this really means is the g of the limit of f of x as x approaches c. So what this says, since we're looking for the limit of f of c, that becomes the limit of f of c, and that's that. So let's see how this works in an example problem. See, and that's the whole thing is, let's apply our theorems to our problems. So take the limit as x approaches pi over 2. Don't worry about following along. It's up there, because you're going to spend more time looking for it. Okay, here's what it says. It gave you the limit set up already. This is how it would be on a test question. Find the limit of cosine 2x plus sine 3 pi over 2 plus x as x approaches pi over 2. Now, the first thing we have to do, we have to apply theorem 10. What does theorem 10 tell us? Is this a composite function? Okay, so if it is a composite function, what's f of x and what's g of x?
F of x is cosine.
No.
No.
Theorem 10, the limit g of x of f of x. F of x is the internal function. So the f of x is what's inside. It's 2x plus sine 3 pi over 2 plus x. That's f of x. The interior function. That's f of x. Is it continuous? How do you know that? You just answer really quick.
Because on the theorem, it said it's
No,
f of x.
it's not there. This is a function. Just look at it. Is 2x a continuous function? Yeah, it's a linear equation. Is the sine function continuous? Yes. So the sum by theorem 1. What does theorem 1 tell us? Theorem 1 tells us that's when if you have two continuous functions and you add them together, then the sum is continuous. If you have two continuous functions and you subtract them, then the difference is continuous. And same with the product and quotient and constant multiple. So the internal function, they're both continuous functions. What's g of x? G of x is cosine of x. Is that a continuous function? Yes. So what theorem 10 tells us, to find the limit of cosine f of x, what we have to do is take the g of x, put it out in front, and then find the limit of f of x as x approaches pi over 2. That's what theorem 10 tells us. So we got to find the limit as x approaches pi over 2 of 2x plus sine 3 pi over 2 plus x. Again, using theorem one. Take the limit of this equation. Well, this is the sum of two functions. So we take the limit of 2x as x approaches pi over 2 plus the limit of sine 3 pi over 2 plus x as x approaches pi over 2. So the limit of 2x as x approaches pi over 2 equals what? Equals pi. What we do is we have 2, in place of x, we put pi over 2. Same thing with the other one. We have sine 3 pi over 2 plus pi over 2. Anywhere we're seeing x, we put a pi over 2. Twos cancel, so we have pi. 3 pi over 2 plus pi over 2 is what? You have a common denominator. So 3 is 4 pi over 2. 5 pi over 2. Which becomes 2 pi. So 2 goes into 4 twice. What is the sine of 2 pi? Yeah, it's the same as the beginning, so that goes to 0. So the cosine at pi equals -1. There's your answer. So that's how you work it out. You have to remember what the theorem 1 rules were. The sum, the difference, the product, the quotient, the constant multiple. Make sense? Let's try a couple of more. The limit as x approaches 1 of the inverse of sine 1 minus x 1 minus x squared. Go and try to figure this one out. Let me put this on pause, see how well y'all do. This is a composite function. Yes, that's the first thing you have to do, because if it's not a composite function, then we don't have to worry about theorem 10. But it is a composite function because our outside function is the inverse of sine, and the inside function is that. Are they both continuous? You said that pretty quick. Why? Why is the inside continuous? Well, since you have a denominator, doesn't this equal 0? Can it equal 0? Well, so if the denominator equals 0, doesn't that mean you have an asymptote? So is it continuous if it has an asymptote? Anybody? It is continuous.
Wait, it's continuous over its domain, right?
What's the domain?
What's domain range of x to?
But the domain of 1 minus x squared is infinity, negative infinity. Okay, let's look at this. What's my first step? Okay, the outside's g of x, the inside's f of x. So since it's a composite function, we take the outside function. Now we take the limit of what's on the inside. What does that tell us? It tells us that there's something in common, top and bottom. So what do? Whenever you have 0 over 0, factor it. So since this doesn't work, we have to factor it. In this equation, the top is already factored. Can the bottom factor out any further? It's a difference of two squares. So it's 1 minus x, 1 plus x. The 1 minus x's cancel. Now we plug in 1 for x. You're absolutely right. Here's what it is. Now, inverse functions. The way inverse functions, what they go, is what angle of sine will give us the answer of 1/2? 30 degrees. So that's the answer. Inverse functions, you have to think of it backwards. This is the answer. What's the question? What's the angle that gives me that answer? Make sense? So you see how theorem 10 is applied here. All you have to do is take the limit of the inside function and then take the outside function to that value. The limit, this is the third one, as x goes to 0, radical x plus 1 times e tangent x. Is this a composite function? Not really. What this one really is, well, it's not really composite as we know it so far. But we do have a function within a function. That's what we're looking at. Because what we could do here is, because they're multiplied, we can split them up. Because notice how this one is not like the other ones where you had a sign and inside the sign you had another. This one is a product of two functions. But Theorem 10 only applies to composite functions. Is radical x plus 1 a composite function? Kind of. What's g of x? The outer function is the square root. The inner function is x plus 1. So for this one, what we can look at is the limit of x plus 1. The x plus 1 is the inner function, so we take the limit of that one. How about the second one, the e to the tangent x? Which one's the outside, which one's the inside function? Tan x is the inside function, right? So here, we have to take the limit of the tan function as x approaches 0. So in the first one, we take anywhere we see an x, we put a 0. Same with the other one. Oh, excuse me. Anywhere you see an x, you put a 0. So square root of 1. What is the tan of 0? Remember, tangent is what? Sine over cosine. So the sine of 0 over cosine of 0. What is the sine of 0? 0 degrees is that point there, which is at 1 comma 0. So the sine value is 0, cosine value is 1. So the answer is 0. So tan of 0 is 0. Square root of 1 is 1. E to the power 0 is 1. 1 times 1 is 1. There's your answer. Make sense? So that's how, again, once you read and understand the theorem, applying them to the work, to the problems, is just plug and play. You have to understand the theorems for it to work. Again, you were taught this in algebra, the Pythagorean theorem. Plug in values, it works. The intermediate value theorem for continuous functions. Actually, it's always been the case, even in algebra. We always talked about a function had to be continuous before we did the intermediate value theorem. Does anybody remember what the intermediate value theorem really talked about? Remember, if the function is continuous, if the function is continuous, then any interval you pick you have f of A and f of B. So it says this, whenever you take two values of a continuous function, then you can find an x to take on any value between there. Now, in algebra, what did we use that for? Because what it said is this. Well, let's put the theorem down. I'll show you what we used it, why we used it. Theorem 11. The intermediate value theorem for continuous functions. So IVT is intermediate value theorem, CF is continuous functions. If f of x is a continuous function on a closed interval, and if y sub 0 is any value between f of a and f of b, then y sub 0 is equal to f of c for some c in that closed interval. So if f of a and f of b have to be defined because it's a closed interval, it's a continuous function, what does a continuous function mean? Don't tell me it's a pencil thingy. What does a continuous function mean? No holes. Has, so yeah, so it's a continuous function, doesn't have any sharp points, doesn't have any jump discontinuities, but it means more things than that. What have we been talking about? If we're talking about if it is continuous, what does that mean? In order to be continuous, the limit has to exist at each point. That means we have to, each point we have to be approaching from both ways. And at the end points has to be able to approach from one side. So if that's the case, then f of c so if you have f of a and f of b, then you can pick a c value anywhere inside that domain. Anywhere inside that domain. It corresponds to an f of c, which is our y sub 0, somewhere between f of a and f of b. Okay, that makes sense. Pretty much common sense, right? What's a use for this? What do we use it for in algebra? In algebra, if f of a and f of b have different signs, then what can you tell me? What does it mean by different signs? Yeah, one's positive, one's negative. It's a continuous function. If they both have different signs, what does that tell us? Then there exists at least one C in that closed interval where the function at C equals 0. Can everybody picture that? Here's A, here's B. F of A, F of B. Do they have different signs? Yeah, down here, this is less than 0, so it's negative. Here, it's greater than 0, so it's positive. The only way that could be true is if between A and B, there's a value C that crosses the x-intercept. I mean, the x-intercept, where the function equals 0.
Can you scroll up a little bit, because I understand what you're saying, but what is that E symbol, where you said some
Oh.
seeds, what is that? Yeah, what is that? What
Is
that
contained within,
contained within? Okay. Is that a
or
Greek letter?
an element of. No, it's just a math symbol we use.
Okay, so it just means it's contained
Yeah.
within. It's not like.
Well,
that's
it's a
what-
symbol from logic, from modal logic. It's just, it tells us that it belongs in this set.
Okay.
And eventually that was changed to that. It just looks nicer when you do that. But it only works. It only works if it's a continuous function. And it doesn't tell us how many or where they are. It just tells us that at least one exists. Again, that doesn't prove us too much, but how about if f of A and f of B are both positive? Is there an x-intercept there? Yeah, we don't know. It's just that if they're opposite, we can tell it. But what if the function looked like this? If they're both the same sign, we can't be sure of anything. But if they're opposite signs, then we know at least there's one x-intercept. So that's what it's saying there. And this x-intercept is called the root. When you're asked to find the solution, this is a side note. When you find a solution to an equation, what are you actually finding? You're finding the x-intercepts, where it crosses the x-axis. Well, that's also called a root. It's also called a factor. All of those really mean the same thing. Because if you think about it, x squared plus 5x plus 6, if it equals 0, what are my factors? Well, I could factor it as x plus 2 times x plus 3, which means x equals -2 and negative, those are my factors. So it means the same thing. Those are also my x-intercepts because it equals 0. And that's just from algebra, so we know what we're looking at. So once with the intermediate value theorem, if we have two values that have opposite signs, then we're guaranteed we have at least one root, one solution. Now, a consequence for root finding. The solution of the equation or the function is a root. If the equation, oh yes, another thing I forgot. Yeah. It's also called a zero. What is that? Is a root if the equation of the equation not of the equation or 0 of the function f. The solution of the function f of equals 0 is a root, or it's also called a 0 of the function. But again, it doesn't tell us where they are or how many we have. It just tells us that it does exist. Example 10. Show there is, I can't say R, is a root for show there's a root for this function between 1 and 2. Again, the first step is always understanding what the question is asking. What is this function going to look like? What's the graph of that function? What kind of function is it? It's a cubic function. What do cubic functions look like? Something like that. So cubic functions can have how many solutions? It can have at most 3. They can have 2 solutions. Or they can have 1 solution. Do we know how many we have? No. We won't know until we actually graph it or we set the function equals 0 and factor it out. But what is it saying? Show that there is a root for this function. What is it asking us to tell? No. That's what you think it's asking. It's just saying, show there is a root. How do we prove that there's a root? Well, if we take f of x, set that's x cubed minus x minus 1. If we take f of 1 and f of 2, and according to the intermediate value theorem, if they have different signs, then we know there's at least one x and 1 root between there. So we have 1 cubed minus 1 minus 1. So 1 cubed is 1, minus 1 minus 1 is a negative 1. Those cancel. 2 cubed minus 2 minus 1. 2 cubed is 8, minus 2 minus 1. 2 minus 8 minus 2 is 6, minus 1 is 5. By the intermediate value theorem, since they have different signs, then there's at least one x-intercept between there. That's all you have to do. It didn't ask, it never asked anywhere, what are the intercepts? How would you, okay, if I did say, find me the x-intercepts, how would you find it? Well, since it's a cubic function, we can't use factoring methods, so to speak. We'd have to use Descartes' rule of signs. We have to figure out, do the synthetic division. Y'all remember that from algebra? How many positives, how many negatives, how many complex zeros will I get? You don't need a calculator. This is all basic algebra. You're too dependent on that calculator. The first thing you did was grab it.
What was the question?
How many positive, how many negative, and how many complex, how many zeros, period, do I have? That's how many, but how many of each? How many positive, how many negatives, how many complex zeros, how many zeros? Positives. Descartes' rule of signs says, count the number of sign changes there are. How many of them are there? This is a positive number. It's changing to a negative. That's one sign changes. Negative, negative. So we have one. So that means we're guaranteed one positive solution. How many negatives? Well, to find the negatives, we change all the x's to negative x. Negative x cubed makes it negative x cubed. Negative negative makes it a positive. So how many sign changes here? There's 1, there's 2. So we're going to have 1 positive and 2 negative solutions. In other words, our graph will look something like this.
Yeah, I just found the negative ones again.
Take the function, anywhere you see an X, change, put a negative X in its place. And then count the sign changes. Remember, I said first day of class is algebra is gonna be the thing that kills you in this class.
Oh, question.
Yes,
Do we not flip the negative sign on the -1?
how? What made it change the sign? It's a constant.
Okay.
All you do to find the negative is put negative X in place of X. So I know I'm gonna have two negative answers. And since we just found the intermediate value theorem between 1 and 2, I know there's an answer somewhere between there. The rational zero theorem. Every polynomial looks like this. The rational zeros say, it tells us, take the last term, the constant, divided by the leading coefficient, and factor them out. So in our case, our polynomial is x cubed minus x minus 1. The a sub n is 1. So it's -1. Now we have to take the positive and negative of -1, which is positive and -1. And we use synthetic division to see what that gives us. So our synthetic division, this is our coefficient for x cubed, x squared, x, and our constant. Remember, our function was x cubed minus x, so we have to find the coefficients. Bring the first one down. Multiply -1 times 1, put it there. Add those two. -1 times -1 is 1. 1 minus 1 is 0. -1 times 0 is 0. We're looking for an answer of 0 here. One times 1 is 1. Okay, so now this tells us that we don't have any integers as our answers. So we have to use another method. That's more complex. So what this tells us is our answers are not gonna be just like 1 or 1.5, our fraction, it's gonna be more complex. And we know that because the answers have to be between 1 and 2. And somewhere between there. It could be something like 3/19 or something like that. But that's all algebra. All the intermediate value theorem does is tells us that 1 does exist there. Okay, how about this one? 2x plus 5 equals 4 minus x squared. So this has a solution. And let's just show it. This is how we do it now. So what does that mean? If it says show this has a solution?
Find the zero.
Find the zero, yeah. It tells us there's an x-intercept. So how do we do that?
Then move on.
Very good. First step, it has to be set equal to 0. So I move the x squared over, so it's plus x squared and minus 4. Then what do you do? Remember, use some of the
You
theorems that
combine
we've had
like
so far.
terms.
What's that?
Oh no, I was gonna say you combine like terms, but never mind.
Mm-mm. Well, we could say we have two separate equations here. What's the domain of this first one? What do we know about square roots? What can they not be? Can't be negative. So the smallest it could be is 0. So that means we have to see what makes inside here set equal to 0. So the smallest x can be is negative 5/2. So the domain of g of x, negative 5/2, comma, infinity. And how about that one? Remember, set these equal to 0. So we have x squared equals 4. So x equals plus or minus 2. Very good. But we want it to be greater than 0. Is 0, 2? Is this domain inside this one? Remember, composite function? So we're looking for the one that's inside the other. 0, 2 is inside here. So we use x1 to be 0 and x2 to be 2. Why do we do that? Because we needed an interval inside the bigger domain to check to see if it has an x-intercept. How do we find if it has an x-intercept? Well, plug in the values. And see if they have different signs. Now, the function is this whole thing here, not just x squared minus 4. Because if we just plug in x minus 4, you know it equals 0. So we use the whole thing. Two times 0 plus 5 plus 0 squared minus 4. So we have the square root of 5 minus 4 so we have the square root of 5 minus 4 negative 1.76. Oop, I'm sorry, that said 0. Negative 1.76. Do the same thing at 2. Square root of 2 times 2 plus 5 plus 2 squared minus 4 4 plus 5 plus 4 minus 4 4 minus 4 cancel. So by the intermediate value theorem, since they have different signs, then we know there's at least one x-intercept in there. That's all it's asking. So again, so if you're given an equation like this, we have two different functions. Here's g of x and here's f of x. Solve them both and then find the internal domain and use those values. Any questions so far? Yes.
Why did, do
All right. I took both of these f of x and g of x, set them equal to 0. And I found the domains. This one's from negative 5 over 2 all the way to infinity. This one is from 0 to 2. So the inter one, that's what I'm using. Now, can we make continuous functions, all of them, can we make them, or if they're not continuous, can we make them continuous? Can we make functions continuous that are not continuous? Continuous extensions what I'm saying here is this. Can we make this a continuous function? Okay, thank you for reading. You were reading ahead. Try to put your notes away and then answer my questions. Again, I don't want you guys to read your notes while I'm in the class here. I want to see what you know, not what I gave you to know. I saw you reading up ahead and everything, so that's why I'm not going to listen to your answers. What this graph looks like right now is that we have an asymptote. It's, first off, is it continuous everywhere except at one point? Yes. So we know that as long as x does not equal 0, it's continuous. If x doesn't equal 0, then we know our function is 1 over x. What if we say now when x is 1, the answer is 0? Does that make it continuous? Yes. Because now every point is now taken care of. That's what this is all about. Is once we locate at what point, no, this is, I'm sorry, at 0. When x is equal 0, the value is 0. We know it's continuous on its domain there, but this is at the asymptote. We can define a value at the asymptotes. Let's look at an example here. Not that one. Well, we started off the chapter with this question. Well, this first two sections.
Let's do chapter 5 or chapter
Section 5.
6?
Does this look familiar? Okay, if so, what do we do with this function? Does the limit exist at this function? What's the only value we have trouble with? Value. What value for x? We can't have a 0 on the bottom, so what happens at 0? Is what? It does. Because remember, this is a limit. Does the limit have to exist there? No, but it does have a value. What's the value? This is how we started off, by using the squeeze theorem. Because with this graph, as x gets closer to 0 from both sides, the value gets very close, then at 0, it's undefined, and it keeps on going. But the limit exists because they both approach the same value. Is it a continuous function? No. Does the limit exist? Yes. So we can make it a piecewise defined function. This is true whenever x does not equal 0. If we define this one as 1, when x is equal to 0, now the whole thing's taken care of. That is the whole purpose we're looking for here. Because even though there's a hole there, the limit exists, but it's not a continuous function. We define it when x equals 0, y equals 1, so now it's a continuous function. That's what this last part tells us, is we can make functions continuous, and we have the possibilities. If we have one point, if we have a hole in the function, then we can make it a continuous function. Show f of x has a continuous extension at x equal 2. And here's the function. So do we have an asymptote here? Or how many asymptotes do we have here? Why do you say 1?
Huh?
Why would you say 1?
Cause they have the same. Both square cubes by both.
Okay, well, then it tells us we have 2. Since we have the same square, then we have a horizontal asymptote as well. But look at the denominator. Right now, we're looking at the denominator, we have how many asymptotes? The vertical asymptote is where the bottom equals 0. The bottom equals 0 at x equals plus or minus 2. Right now, we have 2 asymptotes. Now, all it wants us to do is look at this one at x equals 2. So let's look what happens when we take the limit as x approaches 2 of our function. Two squared plus 2 minus 6. 2 squared minus 4. 4 plus 2 minus 6. 4 minus 4. 0 over 0. And that's exactly what we wanted. And what's going to happen is because would we get 0 over 0 if we put negative 2 in there? You can't do it by looking. It's a math course. You have to write it and work it out. So if x equals negative 2, what would you get? Because remember, our asymptotes were at negative 2 and 2. Yeah, so it would be an asymptote, but not 0 over 0. That's why we don't use the negative 2. Remember, we always want, if we have a 0 over 0, that's the best. If we don't have an answer, it'll give us a chance to find an answer. So what do we do if we have 0 over 0? Factor. So that tells us that with both of our equations, they have a common factor involved. Since the bottom is a difference of two squares, it's x plus 2, x minus 2. On the top, we have x and x. The second sign's a minus, so they're opposite signs. And then the first sign's a plus. The bigger number gets the plus sign. What times what is 3? When you subtract them, you get 1. 3 and 2. So however you were taught in algebra to factor quadratic equations. The x minus 2's can cancel. So now we have x plus 3 over x plus 2. Plug in our x value. What does this number represent? We find these things, but what does this number represent in this equation? What this number represents, remember, when x equals 2, we have a hole at y equals 5, 4. So that's the location of our hole. So the hole is at 2, 5, 4. Why is that important? This is important because now we can create a function that's continuous. We use our function, x squared minus 4. Whenever x does not equal 2, and it equals 5 over 4, whenever x equals 2. This is what the function looks like. Our graph of the function looks like. That's the top equation. Whenever x does not equal 2, that's the rest of the graph. But when x equals 2, it equals 5/4. So now it's a continuous function. That's what it's all about. So what this last section tells us is if we have a function that is not continuous on its onset, it is possible. It's not always, but sometimes. It is possible sometimes to make it continuous. by finding the value of what's missing and plugging, making a composite, piecewise defined function.
How do we know this is possible? Defining which one-
Well, to be honest with you, the one we had earlier, something like this, really, if we said that that equals 0 there, that's not, even though all the values would be allocated, it wouldn't be continuous. Because, well, back to the pencil thingy, if I drew here, then I go here, then I have to go back over here. So something like that would be an example of this. We can make it all where all the domains defined, but it's not really continuous. What we're looking for are functions that have holes. If they have a hole, and what constitutes a hole? That's usually a rational function that has the same value canceled out. In other words, if this happens whenever we have 0 over 0 at some x value, so it's an asymptote. All right, that's it for that section.